Okay guys, in this lesson we are going to be studying how coefficients can affect reaction equations, especially in terms of mole ratios. We do have a bookwork associated with this lesson. It's going to be questions 45 to 55 on these page numbers, and we also have a quiz associated with this lesson, so be prepared for that. It'll be focusing on things that we would have learned in the past few days. Our aim today is how is amount of reactant related to the amount of product. I want you to copy that down on your second piece of classwork paper in addition to the homework heading, and then follow it with these do now questions, which we will solve in class tomorrow. So reaction equations include both qualitative and quantitative information. Qualitative information is going to cover things that are qualities rather than quantities, meaning it's going to cover things that are not numeric. But then if it's numeric in any way, that would be quantitative information. So the qualitative information in this equation is the element symbols, which represent all kinds of things about the element. But the quantitative information is really represented by two things. That would be the coefficients and also the subscripts. But today our focus is going to be on coefficients, and that's because when you are doing any sort of reaction equation, the relative amounts of reactants to products is going to be listed by the coefficients. So in this case, a 2, a 1, an invisible 1, and a 2. This 2 is just telling us, it's a subscript, it's just telling us how many atoms of that element are in 1 unit of the compound fluorine, but it doesn't tell us the amount of fluorine related to the products or related to other reactants. All right, so let's take a look at mole ratios. Let's go ahead and look at this equation right here and consider the above prompt. In the following balanced to chemical equation, coefficients have been used. What do they represent? And as I just mentioned, they represent the relative amounts of reactants and products. For example, this is called ethane, by the way. As you know, this is oxygen, and this is carbon dioxide. And of course, lastly, we have water. I'm just pointing those things out explicitly because I'm going to be sort of descriptive in this next part. But basically, I'm going to pay attention to the coefficients, the 2, the 7, the 4, and the 6. Now remember, they do represent the number of moles of that substance, and in this lesson, we're going to consider them as the number of moles relative to other things. So for instance, let's say that you want to go through this reaction and you want to produce exactly 4 moles of carbon dioxide and 6 moles of water. If you were going to produce 4 moles of CO2 and 6 moles of H2O, then you would need 2 moles of ethane and 7 moles of oxygen. Or you could think of it a different way. If I wanted to react 7 moles of oxygen in the presence of ethane, I would need 2 moles of ethane. Or you could say, if I have 2 moles of ethane, how many moles of carbon dioxide would I produce as a result of a combustion with oxygen? Well, again, it's 2 moles of ethane is going to produce 4 moles of carbon dioxide. Or you could say, if I went through a reaction and I produced 6 moles of water through the combustion of ethane and oxygen, how many moles of oxygen did I use? Well, if you produce 6 moles of water, then you must have used 7 moles of oxygen through a combustion reaction. So what I'm doing is I'm finding different and creative ways, both forwards and backwards. I can stay on the left side and compare 2 things on the left. I can stay on the right side and compare 2 things on the right. I could go from right to left and left to right. You can make any comparison you want, because what I'm really pointing out here is that this reaction equation could be thought of as a system of ratios. Or in other words, let's see, 2 to 7 to 4 to 6. 2, 7, 4, 6. That is our system of ratios for this equation. Okay, so let's get back to work. Let's say that I have 2 moles of ethane and I want to know how many moles of oxygen, how many moles of carbon dioxide, and how many moles of water would be associated. So if you have 2 moles of ethane, then you're going with the very basic ratio of 2, 7, 4, 6. If I were going to change that ratio a little bit so that instead of using 2 moles of ethane, like it says in the equation, I'm using 4 moles of ethane, then consider that you're doubling the amount of ethane. But the ratios need to stay the same in order to keep the equation balanced. So if we're going to keep the ratios the same while doubling the ethane, then we'll need to double every other coefficient throughout the entire system of ratios. So instead of 2, 7, 4, 6, expect 4, 14, 8, 12. But here's a challenging one. If I were going to change the coefficient of ethane down to 1 mole of ethane, I would be changing the ratio from 2, 7, 4, 6 to a smaller ratio, an equal ratio, but with smaller whole number coefficients. And I would be halving each one of them. So instead of 2, 7, 4, 6, I would expect a 1, 3.5, 2, 3. What is true, however, is that regardless of the amount of reactants or products, the mole ratio remains 2, 7, 4, 6 for this reaction. And a mole ratio is simply the relative mole amounts of reactants and products in a reaction equation. So we're going to use conversion factors again here rather loosely. A conversion factor we used for the first time during our mass mole conversions lesson, but we're going to use them again here. And the reason is because they just show us a rate in ratios, how much of this you would need to get how much of that. And I'm conscious here that I may be using a new vocabulary word for the first time, and that word is species. In biology, you guys are all well aware of what species means, but in chemistry, species would just mean any unique set of substances. So like ethane is a species, oxygen's a species, carbon dioxide is a species, and water's a species. So this gives me the ability to answer some pretty unique questions, such as how many moles of water would be produced from the complete combustion of 3 moles of ethane according to the following equation. As you may remember, this is ethane. And the other substance they're interested in here is water. So, of course, here's my water. So what they're doing is they're asking me to relate this substance to this substance, and we would need to think of their mole ratios, which in this case are 2 moles of ethane produce 6 moles of water in a complete combustion reaction. So, if I want to know how many moles of water would be produced from the complete combustion of 3 moles of ethane, I'm changing my moles of ethane from 2 to 3, that's going to change my answer from 6 to something higher. In order to figure out the exact amount, I recommend this method. Simply apply the number of moles of ethane that you want in the numerator of a fraction that you form above the number of moles of ethane in the standard balanced equation. So the standard balance says 2 moles of ethane, but you're going to put a fraction bar, and in the numerator put 3 moles of ethane. And from there, we're just going to construct a very simple ratio. And it's going to start out with this term, 3 over 2, is going to be equal to a new term, which in this case is going to be x number of moles of water. So the ratio is 3 over 2 is equal to x over 6. Now, as I go to solve for this ratio, I recommend cross-multiplying. And if you do that, you will find that 2x is equal to 18, and that x is equal to 9 moles. So that means that you would need 9 moles of water to satisfy the answer. Or in other words, when you use 3 moles of ethane in a complete combustion reaction, you will produce 9 moles of water. So this is our final answer, 9 moles of water. Alright, so let's take a moment to practice what mole ratios do mean and what they don't mean. My first example is what mole ratios do not mean. Alright, so let's consider the following equation, which is the synthesis of hydrogen and chlorine to produce hydrogen chloride. A student suggests that according to the ratio shown by the coefficients that 20 grams of hydrogen, right here, would react with 20 grams of chlorine to produce 40 grams of hydrogen chloride. So in short, this student is not correct, and the reason is because when we do these reaction equations and we're looking at the number of the mole ratios, then you can see that we actually have 1 mole of hydrogen with 1 mole of chlorine producing 2 moles of HCl. So the ratio looks correct. It looks like we have 20-20-40 or 1-1-2, but it's not correct because what they've been relating here is they've been relating mass in grams rather than the number of moles. So when we do these equations, we're doing moles, 1-1-2. Those are moles, mole ratios. It's not mass ratios. So that's my short answer. But in a more complicated answer, I'm going to suggest trying to figure out the number of moles represented by each of the masses given. So if I want to know how many moles are in 20 grams of hydrogen, I need to multiply it by the following conversion factor. Essentially, every mole of H2 gas is going to have a mass of 2 because every atom is worth 1. And that also means that the number of moles of hydrogen we have is 10. That's a result of the grams of hydrogen canceling on the bottom and the left, and then the 20 being divided by the 2. So we have 10 moles of hydrogen. Now let's do something similar with chlorine. In order to figure out how many moles of chlorine we have, we need to figure out how much 1 mole of Cl2 would weigh. So 1 mole of atoms of Cl would be about 35 grams, but if you multiply that by 2, it's going to be much closer to 70. So that'll be 70 grams per mole for Cl2. So I altered that to 71 grams per mole because it was just because of rounding, it wasn't convenient, so I made it up to 71. But that does mean that after the grams of chlorine cancel in the numerator and in the denominator, that we're going to be looking at only 0.28 moles of Cl2. Now to come back to center here, just to remind you of what we were doing, earlier in this lesson we were relating the number of moles as being something that's substantive in equations. 1 mole of hydrogen, 1 mole of chlorine makes 2 moles of HCl. And in this long process here, I've just been proving that if you are given mass, it just won't cut it. So I took these masses and I've been converting them into moles. 20 grams of hydrogen makes 10 moles of hydrogen. If I wanted to keep my ratios correct, then I would need 10 moles of chlorine to react with 10 moles of hydrogen. But as I've discovered, 20 moles of chlorine gas really only produces 0.28 moles of Cl2. So we will not get any more than 0.28 moles of Cl2 to react with 0.28 moles of H2O, making significantly less HCl than you would normally expect. So that was a very long drawn-out answer, but probably this would be enough as long as you understand that. All right, so let's do another. Given the reaction of 4 ammonia plus 5 oxygen yields 4 nitrogen monoxide and 6 water, what's the maximum number of moles of water that could be produced when 2 moles of ammonia are completely reacted? Now let's go back to our very standard form for these equations on the previous slide. So we just take a look at the things that we're being asked to compare, which is the number of moles of water to the number of moles of ammonia. So I do know that 4 moles of ammonia can produce 6 moles of water. And I know that in this particular case that we are using 2 moles of ammonia. So I'm going to take the factor 2 and make a fraction 2 over 4. And now I just need to know x, which is how many moles of water would be produced. So our basic ratio equation or proportion is 2 over 4 equals x over 6. And in the next step, you'll see that 4x is 12. And in the next step, you'll see that x is 3 moles, in this case, of water. Okay, let's do another example. Given the reaction equation, methane plus oxygen, 2 moles of oxygen, yields a mole of carbon dioxide and 2 moles of water, what amount of oxygen is needed to completely react with 1 mole of methane? So right now, we already have 1 mole of methane, and they're suggesting that we use a mole of methane. So I bet this is going to be very easy. And they want to know how much oxygen is going to be needed. So normally 2 moles of oxygen is needed to react with a mole of methane, so we want to know how many moles of oxygen would be needed to react with 1 mole of methane. So literally, this is becoming 1 over 1 is equal to x over 2, or 1x is equal to 2. So you would need 2 moles of oxygen, which of course is not a surprise to any of us. And so we've reached the pair up. I want you to copy these down, I think verbatim today, so copy them down word for word. And those will be the second to last thing in your classwork page for your notes. But the last thing in your classwork page would be these summary questions. They're very good. Please copy them down, shorten them as you need to, but we'll answer them in class tomorrow. Thanks for watching.